So let's go ahead and start by talking about the squeeze theorem, which we did use a little bit last time when we were talking about a limit. But I want to give you one example that's not a function of multiple variables to just kind of remind you. And so we can see the picture as well. So here's a very, very common limit you'll see in the first quarter of calculus. Find the limit as x approaches 0 of x squared times sine of 1 over x. And the issue with this limit is that you can't just plug in 0. 1 over 0 is undefined. Sine of something that's getting larger and larger and larger is undefined. But if you think about the sine function, it does this like forever and ever and ever and ever and ever. So if the insides are getting large, the outside of the function value is just oscillating back and forth between -1 and 1. But the fact that sine of whatever oscillates between -1 and 1, or is bounded by -1 and 1, is actually the key piece of information we're going to use the squeeze theorem. And it's a very common thing. So if you see a limit with sine or cosine, it's often an invitation to use the fact that sine of anything is always between -1 and 1. And that's true for sine and for cosine. Think about the graph of sine. It's always topping out at +1, bottoming out at -1. Now, specifically in this example, sine of 1 over x is between -1 and 1. Typically, you need some sort of compound inequality to be able to use the squeeze theorem. You need the thing that you're trying to take the limit of to be in between two other things that we're going to take the limit of. So then the next step is to make the middle part look like the thing you're trying to take the limit of. In this case, it's just going to mean multiplying everything by x squared. So I multiply everything by x squared, I get -1 times x squared. I get x squared times sine of 1 over x. And I get x squared times 1, which I should just write x squared. All right, try to write times 1 there. So now we have the thing we want in the middle, bounded by -x squared on the left and +x squared on the right. And then we're going to take the limit of the two outer things. So I'm going to take the limit as x approaches 0 of x squared. And I'm going to get 0. Because if x is going to 0, so is x squared. Similarly, I'm going to take the limit as x goes to 0 of -x squared. And I'm also going to get 0. And since the limit of this is equal to 0, and the limit of that's equal to 0, the limit of this has to be less than or equal to 0 and bigger than or equal to 0. So we can say by the squeeze theorem, or sandwich theorem, or whatever name you like to call it. But I guess someone wrote something else recently. By the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x also must be 0. It only works if the two outer things here have the same value for their limit. They approach anything different than each other, you can't use the squeeze theorem. Graphically, one second. Graphically, here's what this looks like. So here's the function y equals x squared in red. Here's the function y equals -x squared in blue. And here's the function y equals x squared times sine of 1 over x. And it's stuck between these two functions. And if you zoom further in, you can see that, oh yeah, it's just bouncing back and forth, back and forth, back and forth between x squared and -x squared. But since both x squared and -x squared are getting closer and closer to a y value of 0, there is no choice except for the x squared times sine of 1 over x to also get smushed or squeezed towards a y value of 0. Oops.
So the squeeze theorem is only applicable to sine and cosine?
No, it's not. It's just there often are examples that come up because they're easy to bound. But definitely the example we're about to look at, we're not going to have sine or cosine. But this is a nice, easy function of one variable that will show us, oh yeah, here's an example of the squeeze theorem. Also, just so you all can see, I want to point out that if you just graph sine of 1 over x, that doesn't look like sine, James. Look at this. It's wild, right? It's oscillating back and forth an infinite number of times as you get closer and closer to the origin, right? It just looks like a solid brick of graph, but really it's just like back and forth, 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 back and forth forever. So the limit as x approaches 0 of just sine of 1 over x doesn't exist. It's infinitely oscillating. But this thing gets closer and closer to 0. Cool. Okay, let's look at a different example. Again. So, where'd you go? Yeah, I kind of just had whatever. So the question really comes up when we talk about, say, like the limit as x, y approaches 0, 0 of something like, yeah, I'm gonna make something up slightly different. Hopefully this doesn't bite me back. 3x squared, yeah, y squared over x to the 4th plus y to the 4th. Now try this one. I think it'll work. If it doesn't, we'll find out. So, as we see with many of our limits, if you try plugging in 0 for x and 0 for y, you get 0 over 0, which is an indeterminate form. So if I saw this question on a test and there wasn't any other information, I would start picking paths. I would say, well, let's try y equals 0. If I do that, I'm going to get the limit. We still need to write the limit, but only as x approaches 0, because y isn't approaching 0. Y already is 0. I have 3 times x squared times 0 squared over x to the 4th plus 0 to the 4th. This becomes the limit as x approaches 0 of 0 over x to the 4th, which is going to be 0. I like writing the additional step of saying it's the limit of 0, but you probably could skip that and just say, yeah, I know the limit of 0 is going to be, 0. I can also see that if I try, I feel like this one's not, I feel like I made this, it's okay, I didn't make a mistake. I'm just not gonna try it the way I thought it was. So let's point out that if we try x equals 0, we're not gonna get anything different. We're still gonna get 0 on the top and y to the 4th on the bottom, and that'll be the limit of 0 as well. So that will also lead to 0. I would probably next try y equal to x. So we try y equal to x, I'm gonna get the limit as, you could use either x or y. I'm going to use x because I like using x better. 3 times x squared over x to the 4th plus x to the 4th. That's going to be the limit as x goes to 0 of 3x to the 4th over 2x to the 4th, which becomes the limit as x goes to 0, 3 halves, which is equal to 3 halves. So we're done. We picked 2 different paths that both go through the origin, 0, 0, and we got 2 different values. This means the limit doesn't exist. The limit as xy approaches 0, 0 of 3x squared y squared over x to the 4th plus y to the 4th does not exist. Because we got values along different paths that are not the same. And that's how you should approach any limit unless someone specifically tells you that you know it exists. If you are either told it doesn't exist or told that you just have to figure it out, you should always start with the assumption that it's probably not going to exist and try picking different paths. Now, like we saw last time, sometimes that doesn't work. So I was trying to come up with something that was, sure, we can do that. Okay, I'm gonna change up a little bit. I think what I'm about to do is gonna work. Oh, I know it was. I'm smart. Sometimes we make mistakes. Let's try this instead. I'm using the royal we. We all make mistakes. Let's try this one. I think this will work out. 4x squared times y squared over x squared plus 2y squared. Let's try that. That seems good. I'm pretty sure this is going to be 0, but I'm not 100% sure. So let's try a couple paths. Once again, y equals 0 or x equals 0. I should point out, these don't always give you the same result, but they often give you a result of 0. So I'm going to try y equals 0 specifically. Actually, no, let's try x equals 0 just to change it up. So if I let x equal 0, that's going to give me still y's remaining. And the limit as y goes to 0 of 4 times 0 times y squared over 0 plus 2y squared. That's the limit as y goes to 0 of 0 over y squared, which is the limit As y goes to 0, 0, which is 0. Question?
Aside from most of these coming out to be zero, is there any other reason why you said like you predict that this is gonna be like does not exist? Because I feel like.
Well, so I think this one actually is going to exist.
Okay,
Yeah.
it's because the numerator has a higher.
That's kind of the intuition. Then again, I don't have a super great intuition about exactly knowing if it's going to exist or not. I'm relatively confident that when the degree on top, for lack of a better word, and I would say the degree on top is 4, because you have an x squared times a y squared, I'm adding those powers, whereas on the bottom the degree is 2, because the highest power of an individual term is to the second power. Since the degree on top is larger, I think the limit's going to be 0. That is my gut place, but it's not maybe 100% always true. But I'm pretty sure it's going to be true.
Are there any other like facts or predictions like even like vaguely?
My prediction is most of the time the limit's not going to exist.
Okay.
That's where you should always attack this from. If you're doing a limit as x, y, if you're getting 0 over 0, right? So the first thing you should do first, right, is plug it in and see if you get a number. Like just to kind of off to the side here, just to point out, if someone said, like, what's the limit as x, y approaches 1, 2 of this same expression? Well, that's easy peasy. You plug in 1 for x and 2 for y, and you get 4 times 1 squared times 2 squared over 1 squared plus 2 times 2 squared, which is something. It's what, 16 over 9. Great, that's the limit. I would also point out, just because I've seen people asking, in this previous problem, this function is continuous. So we'll point out this function, f of x, y, equal to 3x squared plus y squared, sorry, times y squared, holy smokes, over x to the 4th plus y to the 4th. The only place this function is undefined is at the origin. It is also the only place it's discontinuous. This function is continuous on its domain. Everywhere except the point 0, 0. Now I want to be extra clear here. This is the wrong way to write that domain. So not this, everything from negative infinity to 0, union 0 to infinity. That would be if your function was a function of one variable and you just wanted to remove 0 as one of the values. Our domain is actually, it's actually most easily drawn, because I was going to write it as a set. It's the set of all points x, y, such that we don't have 0. X and y are both not 0 at the same time. Graphically, it's the entire xy plane except for the origin. So there's your domain. Every single point except for the origin. There's your region where the function is continuous. Yeah.
So for us, the domain is like.
Yes, exactly. Not only count, that is the answer. And if it were me asking this question on test or quiz, I would choose to ask you to draw the domain, because that is probably the easiest way to express it, and it's also the most informative way to think about it. It's probably going to be some sort of circle thing. We'll talk a little bit more about that in a second. But back to this question here. Oh, sorry. So at any other point, the limit will exist. Right? Pick any point that's not 0, 0. The bottom won't be 0, and so the limit will exist. And at any other point, the function value will be just whatever you get when you plug it in. So the limit value and the function value will be the same. That's why it's continuous everywhere else, because essentially anywhere else where you can find the limit, it's probably just going to be by plugging it in. Now, what I'm going to point out is, even though this function, the limit is going to exist at 0, 0, probably, it's still not going to be continuous there, because the function is undefined at 0, 0. So really, when you're talking about where a function is continuous, most of the time in this sort of situation, you're really just looking for what's the domain of the function. We could try, well, I'll amend this one in a second to kind of answer your question even further. So let's see here. So yeah, I could try other paths. I could try like y equals x. I would get the limit as x goes to 0 of 4x squared times x squared. over x squared plus 2x squared. That ends up being the limit as x goes to 0 of 4x to the fourth over 3x squared becomes 4/3, and x to the fourth divided by x squared is x squared. And if I plug in 0, I get 0. And I'm not going to keep beating my head against this wall because I'm pretty sure the limit exists. So here's the intuition. You're going to take, and I always feel like this always feels a little bit like just kind of out of nowhere to me. But here's what we're usually looking for. You're looking to say something about some piece of the numerator being always less than or equal to the entire denominator. So check this out. X squared is certainly equal to x squared, and it's less than or equal to x squared plus anything that's always non-negative, which 2y squared is certainly always non-negative. Also, x squared is bigger than or equal to 0. Because it's non-negative, right? It's x squared. And now, just like with the previous squeeze theorem problem we did, where we're going to take the inequality we have and then try to make the middle part look like the thing we're trying to take the limit of, that's what I'm going to do. I'm going to do it in 2 steps here. First, I'm going to divide everything by x squared plus 2y squared. So 0 over x squared plus 2y squared is still going to be 0. X squared over x squared plus 2y squared. And x squared plus 2y squared over x squared plus 2y squared. I'll point out that the right-hand side of this compound inequality is 1. The left-hand side of this inequality is 0.
How do we choose the right-hand side again?
So you're basically choosing the denominator. And I'm saying I know that x squared, which is something that's occurring in the numerator, is less than or equal to the denominator. I could have just as easily picked y squared in the top instead of x squared. That would have also been valid. Okay. So now I have that 0 is less than or equal to x squared over x squared plus 2y squared is less than or equal to 1. What am I missing? Sorry, you can't see that probably. Apologies. I got way up there. What am I missing from this fraction that's still in my original thing I'm trying to take the limit of? 4, and also what else? In the numerator. Right. So I'm going to multiply everything by the thing I'm missing, 4y squared. So multiply by 4y squared, and I get 0 times 4y squared less than or equal to x squared over x squared plus 2y squared times 4y squared less than or equal to 4y squared. Now we have the thing we want to take the limit of in the middle. Yeah, I know it's written slightly differently. That's okay. Now I'm going to take the limit of the other outside parts. So the limit as x, y approaches 0, 0 of 0 is, I think, 0. Pretty sure it's 0. And more importantly, the limit as x, y approaches 0, 0 of 4y squared. Well, if y is getting closer and closer to 0, then 4 times y squared is also getting closer and closer to 0. So since the limit of this part's 0 and the limit of this part's 0, then the limit of the middle part has to be squeezed to 0. So I think I can squeeze this in here. By the squeeze theorem, the limit as x, y, wow, that's terrible, James, approaches 0, 0 of this middle part here, which is 4x squared y squared over x squared plus 2y squared, is in fact 0. And that's how we're using the squeeze theorem to prove that a multivariable limit does exist. I will point out, so this limit does equal 0. I will also point out that the function f of xy equal to 4x squared y squared over x squared plus 2y squared is continuous everywhere except the origin. And the reason it's not continuous at the origin is because it's not defined at the origin. But since the limit as xy approaches 0, 0 does in fact exist and is equal to 0, you could amend or extend this function so that it is continuous everywhere. So I can make up a new function, a new piecewise function like this. I could say, well, let's say that g of x comma y is equal to the function we had before, 4x squared times y squared over x squared plus 2y squared, when x comma y is not equal to 0, 0, which is probably how I should have written it before when I was doing the domain, but I didn't. And then it is equal to 0 when xy is the origin. And that is continuous everywhere on the entire xy plane. Right? Not the set from negative infinity to infinity, not all real numbers, all pairs of real numbers in the xy plane. Kind of neat. Okay. As much as I would love to say more about this, we should really start talking about partial fractions. Why do I keep saying partial fractions? Partial derivatives. Oh my goodness. Last thing I want to say about this actually. So we can also see this graphically, which I think is kind of cool. So if we look over here at the three-dimensional graphing, and I had some different ones here, so let's actually fix this. I have 4x squared y squared. And I have over x squared plus 2y squared. And then it was bounded above by 4y squared. Now, it might be kind of hard to see, but check it out. That purple thing is always bigger than or equal to that green thing. Right? And then be like, ooh, come on, James. Right? The green thing, although they're pretty close to each other, right? It's always the green thing, the green surface is the better word there, is always below the purple surface. And the green surface is always above or touching the blue plane z equals 0. And then we can see that as we approach the origin, well, that purple surface, the only thing it can do as you approach the origin is get closer and closer to the point 0, right? If we look at the point 0, 0, 0, which you maybe can see, I don't know. That's, you can kind of see there, but right, like, can I make these like translucent somehow? Maybe, there we go, yeah, cool. They don't look, I mean, kind of, okay, yeah. Right, you can see that no matter how we approach the origin on the purple surface, we're getting smushed down to 0. And so since the green surface is below it, it's also getting smushed down to 0. Very, very much like the squeeze theorem in the other problem. So that's why this is it's not as easy to see with these three-dimensional surfaces, I don't think, but the same idea persists. Right, we've got this idea of, oh yeah, the thing that's above is going to 0 or whatever value, the thing that's below is going to 0 or whatever value, and the thing in the middle has no choice. All right. Yeah, let's talk about partial derivatives, because that is definitely, I know there's a lot of things to talk about, but that's probably what we should spend some time talking about. Partial derivatives. Sure. Cool. Also, just as a reminder to everybody, I have office hours all the various times, and now the drop-in is open starting yesterday, so you can come see me in math drop-in on Mondays and Wednesdays from 10 to noon if you have time there, and then also the other usual office hours. So let's start here. Partial derivatives. Partial derivatives, once you get the hang of them, are really, really not terrible at all. They just take a little bit of getting the hang of. So let me ask you all a couple questions. What's the derivative of 5x? Cool. And then also, what's the derivative of, say, I don't know, 4x to the third? Cool. Now I'm going to do it slightly differently, but you're all right. I'm going to write it as 4 times 3x squared. That's what's really happening, right? The constant multiple, I like to say, hangs out. And then we take the derivative. In fact, there's even an additional step we can write. We say it's 4 times the derivative of x cubed. And that's equal to 4 times 3x squared, which then, of course, we would actually write as 12x squared. But what we're really doing is we're taking the derivative of the function part, and then we're multiplying it by the constant that's just sitting out here. So importantly, right, the derivative of 4 here is not 0. That 4 just doesn't go away. It's a constant, but it's a constant multiple. Whereas if I said, what's the derivative of, like, say, x squared plus 7, the derivative of x squared is in fact 2x, but the derivative of 7 on its own, not attached to any variable, is, and then you see 2x. Okay, so here's why we're saying this. The whole idea with partial derivatives, I keep wanting to say fractions, is that we are going to essentially pretend like the variable we are not differentiating with respect to is a constant. So let's look at an example. Yeah, let's use a new page. So let's say we have a function f of x comma y equal to x to the 4th plus y cubed plus x squared times y to the 5th. And I'm going to take some partial derivatives here. And yeah. Maybe. So a couple ways of writing a partial derivative. You can either write it as fx, meaning we're going to differentiate with respect to x, or you can write it as del f del x. Yes, that's not a d, that's a del, which is just a curly looking d. If you write them, they look the same, no one's going to care. But I will try to be specific, right? If it's a partial derivative, you should write a del. If it's a regular derivative for a function of one variable, you should write a d. So here, the partial derivative with respect to x, well, the derivative of x to the 4th is 4x cubed. Y is a constant because we're letting x change and we're holding y constant. And the derivative of a constant to the 3rd power is 0. Right? What's the derivative of 2 cubed? Oh, it's 0. And then x squared times y to the 5th is like x squared times 7. And the derivative of x squared times 7 is 2x times 7. Or 2x times y to the 5th. Y to the 5th is just hanging out. It's a constant as far as differentiating with respect to x is concerned. On the other side of things, the partial derivative with respect to y, and just as some notational reading stuff, we read this as fx, not f sub x, not f of x, just fx. You don't say anything in between them. Here we've got fy, or del f del y. Now different. Oh, and I should rewrite this as 4x cubed plus 2xy, right? You don't really want to write the plus 0 in your answer. It seems unnecessary. So now differentiating with respect to y, the derivative of x to the 4th is 0. Derivative of y cubed is 3y squared. And the derivative of a constant times y to the 5th is that same constant times 5y to the 4th. If I was trying to write this a little more nicely, I would write it as 3y squared plus 5x squared times y to the 4th. Typically write actual constants out in front and then variables after that, usually in alphabetical order, although it doesn't actually matter, it's just standard practice. Let's find some second partial derivatives. By the way, just like with regular derivatives, regular or partial derivatives, second partial derivatives, third partial derivatives, you're just doing the same thing over and over and over again. So I'm just going to differentiate. If I want to find fxx or del squared f del x squared, I'm just taking my partial derivative with respect to x and differentiating with respect to x again. So now, excuse me, taking the derivative of this with respect to x, the derivative of 4x cubed is 12x squared. The derivative of 2x times a constant is just 2 times that constant. Why don't you all find fyy? Or del squared f del y squared. And you're going to look at fy, the partial with respect to y, and take the derivative of that with respect to y again. Yes, right after class, yeah, right after class, I have office hours in C class.
Oh.
I think. So it's, so you know where like the flagpole is over here? Right over there, like the flagpole that you can't quite see, but like the one that's right over in front of the coffee house. There's stairs there, you go up those stairs, you just veer slightly to the left, and there's C class, also called El Centro. And I'm like, you asked them, like, is James here? And I'm like in the back. Yeah, come find me. Yeah, and let me just double, now I'm like, that is where I am, right? Let me check. Still getting used to my, every quarter it's a new schedule. I'm like, yeah, what am I doing this quarter? Okay. Let's see. Yes, that is, today is Wednesday. Today is Wednesday. Yeah, okay. That's where I am after class. So this partial derivative should be 6y plus 5x squared times 4y cubed, which I would write as 6y plus 5 times 4 is 20x squared y cubed. You can keep doing this forever. Well, I mean, with these kinds of things, you'd actually run out eventually if you wanted to. But these are typical ones. First partial derivative, second partial derivatives, and also the mixed partial derivative. So we could also take the partial derivative fxy, meaning you differentiate with respect to x first, and then with respect to y second. Now, pay attention for a moment. This is equal to del squared f del y del x. Yes, the order is looking like it's reversed. Because when you write this notation here, you read from right to left. This really says the derivative with respect to y of the derivative of f with respect to x. So reading it this way, you would do del f del x first, and then you take the derivative of that with respect to y. Same way you read it this way. You do the derivative with respect to x first, and then the derivative of that with respect to y second. So I'm going to write this as del y of del f del x, which is 4x cubed plus 2xy to the fifth. And now I'm going to take the derivative of that. So I did x first, and now I'm going to do the derivative of that with respect to y second. So I'm going to get the derivative of 4x cubed with respect to y is 0. The derivative of 2x times y to the fifth, well, the 2x is acting like a constant. It gets to hang out. And the derivative of y to the fifth is 5y to the fourth. So we end up with 10 times x times y to the fourth. Here's something that's great. Now, you still need to get the order right here. But if you happen to get it backwards, that's almost never an issue. Because if we go the other direction, say we find the mixed partial fyx, or del squared f del x del y, which is the same as del x of del f del y, which is the partial derivative with respect to x of the first partial derivative with respect to y, making the partial with respect to x of 3y squared plus 5x squared y to the fourth. The derivative of 3y squared with respect to x is going to be 0. The derivative of 5x squared times y to the fourth, well, the y to the fourth is acting like a constant, and the derivative of 5x squared is 10x times its constant multiple, and oh look, I got the same answer. And that is generally true. Most of the time, and I'll expand on that in a minute, if you take the mixed partial in either direction, you should get the same answer. That's not always true. There are some functions where you can make that, but they are really they're weird. The easiest example of a function where this is not true is some sort of piecewise function that's kind of hard to define. And one more second. And this is what's called this is called Clairaut's theorem. This says these two partial derivatives are equal to each other when you have certain continuity conditions. And in this class, this should always be true. We're not going to really encounter functions where this isn't true.
So if we are doing a kind of problem like this, where this is the case where we switch it to the same time, if we were solving it, we actually solve it the wrong order, but we get the same answer, still get full credit.
That's the question I can't answer. I would say no. If it were me, if I was looking close, if I was not just looking at your answer, I was looking closely at your work, and I saw that you did it out of order, I would probably knock you off because you've technically done the wrong thing. Yeah, you've arrived at the right answer, but I mean, right? We want to get the right answer for the right reasons, not the wrong reasons. Yeah. So, this is really kind of the gist of partial derivatives. Let's look at some other examples. In fact, there was a couple from the homework that people had asked me about, so let's look at those. So this is numbers 33 and 35 from section 9.2. So let's look at, I keep wanting to write too high. So 9.2 number 33. This is, our function is f of x comma y is equal to the natural log of x plus the square root of x squared plus y squared. And then we're gonna do more than just that. So they've asked us to find fx evaluated at 3, 4, meaning the partial derivative with respect to x, and then we want to plug in the 0.3, 4. Essentially, you're trying to find, no, that's not a good example. Never mind. So let's find like more than just fx. So fx is okay. I might, before I did anything, reimagine this as the natural log of x plus x squared plus y squared to the 1/2 power, just to make it a little bit easier for myself. So let's find fx, the partial with respect to x, or del f del x. You don't need to write both of these ever, really. I'm just writing both of them so you get familiar and comfortable with both of them. Excuse me. It's kind of like writing y prime versus dy dx. Either one is fine, just whatever you like. So partial with respect to x, I've got the natural log of some stuff. And the derivative of the natural log of some stuff is 1 over the stuff. Then we have to multiply by the derivative of the stuff. The derivative of x is 1. The derivative of x squared plus y squared to the 1/2. So the derivative of some stuff to the 1/2 power is 1/2 times your stuff to the negative 1/2 power times the what of the inside? The derivative of the inside. Well, I should say the derivative with respect to x of the inside. So the derivative of x squared plus y squared is going to be plus 0. Gross. Could we simplify this? Sure. Should we simplify it? Not really. If I was going to simplify it, here's what I would do. I would rewrite it as 1 fraction. I would leave my denominator as is. And the only thing I'd really do in the numerator is notice that 2x times 1/2 will just be x. So I would rewrite the numerator as 1 plus x times x squared plus y squared to the negative 1/2. But really, that's all I think you should really do here. Is there more you could do? Sure. Is there more you should do? Not really. Before we go out plugging in points and things, let's go ahead and find fy, the partial with respect to y as well. Which, now that we've done fx, I think is actually going to be a little bit easier. Because I still know that the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. The 1 over part is still going to be the same as it was before. Now the derivative of the stuff is the derivative with respect to y. The derivative of x is going to be 0. And the derivative of x squared plus y squared to the 1/2 is going to be 1/2 times x squared plus y squared to the negative 1/2 multiplied by the derivative of the inside, which this time is going to be what? 2y. And then if you wanted, you could rewrite this as this whole thing in parentheses on top. I would cancel a 2 there and get y times x squared plus y squared to the negative 1/2 over x plus x squared plus y squared to the 1/2. And then, to answer their silly questions, if I wanted to find fx at 3, 4, I would just plug in 3 for x and 4 for y. I would maybe make a mental note before I did that. 3 squared plus 4 squared is how much? Everyone's favorite square number, 25. And then the square root of that is going to be 5. So what I'm going to get here is I'm going to get 1 plus 3 times 25 to the negative 1/2 over 3 plus 25 to the 1/2. And I could leave it like that, and I probably would leave it like that if I was taking a test and I didn't have a lot of time. I'd be like, yeah, there you go. But if you want to simplify this, it's going to be 1 plus 25. Let's look at the bottom. 3 plus the square root of 25 is 5. On top, 25 to the negative 1/2 isn't 5, it's 1/5. And sure, there's other things you could do here. If you really want to make this look as nice as possible, I would probably, I don't know. I'm not sure what I would do really. I would probably multiply the top and bottom by 5 and get 5 plus 3 over 8 times 5. And then I'd have 8 over 40, which is 1/5. So it does simplify pretty nicely. Let's do it down here as well. So Fy of 3 comma 4. So I'm plugging in 4 for y, so I'm getting 4 times 25 to the negative 1/2, which we know is going to be 1/5, over still 3 plus 25 to the 1/2. So now I'm getting 4/5 over 3 plus 5, which is 4/5 over 8, or 4/5 times 1/8, which ends up being 1/10. What does this mean? It means on this surface, at this point, 3 comma 4, the slope of the tangent line in the direction of x is a slope of 1/5. The slope of the tangent line in the direction of y is a slope of 1/10. Sure. To kind of, we have not a lot of time, to kind of expand on that idea just a little bit. You don't need to write this down, I just want to kind of show you a picture really quickly. For this function, f of x y equal to 9 minus x squared, if we look at the point 1 comma 2 comma 4, where x is 1, y is 2, and z is 4, there. We can look at the partial derivative in the x direction, which is the x direction towards you, right? If I'm moving in the x direction, I'm moving in the positive x direction, which is the direction towards you. If I'm moving in the y direction, I'm moving to the right, because I'm moving in the positive y direction. So if someone says the x direction or the y direction, they mean the positive blank direction, whether it's x or y, or z, I guess. Usually x or y. So I'm moving in the positive x direction towards you. Am I going down the surface or up the surface? Down, right? Because I'm kind of right. I'm on the front side of the mountain, and I'm moving away from the middle. I'm moving down. Similarly, if I move to the right, I'm also going to be moving down. So I would expect that the slope of the tangent line in either of those directions would be a negative slope. And it is. If we look at del f del x, it ends up being negative 2x. If you plug in the point 1 comma 2 comma 4, where x is 1, y is 2, and z is 4, if I plug in 1 specifically for x, I get a slope of negative 2. In a similar way, in the y direction, my partial derivative is negative 2y. And if I plug in the point 1 comma 2 comma 4, the slope in the y direction is negative 4. So it's actually steeper down to the right than it is to the front, which makes sense, right? If you ever like hiked on a hillside, not every direction has the same steepness, right? Some ways are really steep and some ways are really flat. Yeah. That's all I want to say really about that. What can we say in the last? Oh, there was another problem here to look at. Let's look at one other one here. Yeah, let's look at this. Oh, this is a good problem. So here's problem 35 from the same section. Now our function is a function of 3 variables. F of x, y, z is equal to y over x plus y plus z. And let's go ahead and find fx and fy. And we'll do these in 2 different ways, just kind of point out a couple different things. So I want to find, yeah, sure. Let's find fy first. To find fy, I could use the quotient rule. I can say, well, I've got a quotient. The derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. Okay, everybody show me on your fingers. What's the derivative of the bottom? Polite fingers, please, polite fingers. Yeah, because there's only one, right? The derivative of x plus y plus z is 0 plus 1 plus 0 with respect to y. Right, if you ever be like, if I ever say like, don't use that finger, you know the answer is 1 because, okay. Divided by the denominator squared. And then if you want to simplify this, this becomes x plus y plus z minus y, which is just x plus z over x plus y plus z squared. Now I will point out, this might not have been the best way to do it. We could have instead thought of our function as y times x plus y plus z to the negative first. If we do it that way, I'm going to do fy again. Then we would have to use the product rule. Derivative of y is 1 times the other piece plus y times the derivative of the other piece. The derivative of some stuff to the negative first power is going to be -1 times your stuff to the negative second power times the derivative of the insides, which is going to be 0 plus 1 plus 0. This doesn't look particularly better to me, but it's fine. It's a way of doing it. And if you simplify this, you could make it look like that. I will point out, because I think it's worth pointing out, this is 1 over x plus y plus z minus y over x plus y plus z squared. The minus comes from -1 times y. The denominator comes from x plus y plus z to the negative second to the bottom. And then if I multiply the first term by x plus y plus z over x plus y plus z, so I get x plus y plus z over x plus y plus z squared minus y over x plus y plus z squared. Oh, look, I'm exactly back to right there. So you get the same thing either way. It's just not always going to look the same unless you do the work to make it look the same. On the other hand, if I'm finding fx or del f del x, if I prefer to write it that way, I would probably use this version of it because I only have an x in the bottom. So I'd rather write it like this and kind of think of it as just well, my y is a constant multiple, going to hang out. So my derivative is going to be y times the derivative of x plus y plus z to the negative first, which is going to be -1 times x plus y plus z to the negative second, and then times the derivative of the inside, which is 1 plus 0 plus 0. If you really wanted to rewrite this in a nicer looking way, you could say it's -y over x plus y plus z squared. And then you can plug in a point if you wanted to. But I should stop talking. It's 2 o'clock.